All right, so the population of a town is decreasing at a rate of 4% a year. If the town has a population of 53,000 in 2020, at this rate, what will be the town's population in 2030? And what was the town's population in 2010? So first, the key thing here is that the town is decreasing at a rate of 4% a year. And the rate we can think of as our R value, if we think of this as a geometric sequence. And if I go up here, in general, if something is decreasing by a percentage, we can think of our R value being 1 minus the percentage we're losing. And remember, a percentage just means out of 100. Hence, you see this 1 minus n over 100. And so if we're losing 4% a year, we can think of our common ratio as being 1 minus either 4 out of 100, which is what 4% means, or what I like a little better, 1 minus 0.04, or even better in my opinion, 0.96. So there's our common ratio. Every year, if we think of it as a geometric sequence, we're multiplying by 0.96. So instead of thinking of it as losing 4% a year, we're keeping 96%. But now we can directly apply it as a geometric sequence. With that said, one perfectly fine way that I will avoid in the end is to imagine 53,000 being our term 1. And then we have term 2, term 3, and so on. However, if we're locked into thinking of it as a geometric sequence, we really can't have negative terms and whatnot. As well, that's my start, 53,000. And I'd rather it be year 0 years from now, if we think of now being 2020. And there's nothing inherently wrong with keeping it as term 1, but 0 makes it easier to think about how things are changing. And so I'm going to call this U0 or time 0. And still the same idea, we're multiplying by 0.96 every time we go from one term to the next. But then I'm thinking of this being term 1, which is 2021. This is term 2, which is 2022. As well, I can now go backwards because I'm not inherently thinking of this having to be a geometric sequence formally. And so this I can think of as being U negative 1, which is the population in 2019, 1 year before the start. With that said, I can now formalize this as a function. If I wanted to use the variable u, which I don't really have to, I could say un equals my start, 53,000. But because my start is 0, it is multiplying by the common ratio, but it's not going to be n minus 1. That's only if we're assuming the first term has to be term 1. If I'm having just be term 0, that's my new equation. And that's kind of what's being discussed here. If we modify our most formal way of showing a geometric sequence into this, we can start at term 0, which is much more pleasant usually for an initial amount. And so that's the equation I'm going to use. And this makes it easier for me to see, for example, if I want to find the population in the year 2030, that's just 10 years from 2020. And so that's 10 years from 0, which is 10. And so the year 2030, will be, you can think of it as my 10th term, imagining that I'm starting at term 0, which would be 53,000 times 0.96 to the power of 10. I don't have to worry about thinking about what the term number is. It's 10 years from 0. And you go to your calculator and I get approximately 35,236. And since this is not a geometric sequence, or not formally, I can think about negative terms. And so the year 2010 would be U negative 10 years before 2020, which means it's going to be the same setup, 53,000, 0.96 to the power of negative 10, which I can just input into a calculator, and I get approximately 79,719. Keep in mind, if I decided to call this term 1 instead of term 0, then everything would be similar, except this would actually be term 11 in the end, and this would be term negative 9, which is less obvious, I think, it's a matter of opinion, about where those numbers came from compared to starting at 0, where 10 years in the future is 10, 10 years in the past is negative 10. So half-life questions. So first, when we say the half-life of something, in this case, is 5,700 years, that means every 5,700 years, half of the amount of this case of carbon-14 is left. So every 5,700 years, whatever this value of u is, I'll say un, we multiply by a half. Multiplying by a half, same as dividing by 2. So really the question is, how many times over 22,800 years will this amount of carbon-14 be cut in half? And so the first thing I really want to think about is, well, how many times does 5,700 go into 22,800? And so let's divide. And conveniently enough, we get exactly 4, which means after 22,800 years, the amount of carbon-14 in a living being will be cut in half 4 times. And so now I can formalize this here by saying U, if I want U to represent the amount of carbon-14, the initial amount was 127. It's being divided by 2, same as multiplying by a half. But how many times? Well, again, I could go back to this, 22,800 divided by 5,700. That's my power, but I've already figured out that's 4, so I like this better. 127 times a half to the power of 4. Because that's literally showing what I've mentioned already, that the initial amount of carbon-14 will be cut in half, multiplied by half, 4 times. Now again, at this point, it's just a matter of our calculator, and we get approximately, after 22,800 years, or after taking that initial amount and dividing by 2 4 times, we get approximately 7.94 grams. Right, so the last question. The starting salary of an electrical engineer is $72,000 US, and on average, their salary increases at a rate of 3.7% per year. So going back to the first question, I can think about my rate of growth being 1 for plus 0.037, which just means all the money we had before, 1 as a percentage is 100%. 100% plus 3.7% is what we're really doing here. But instead of thinking of it as percentages, instead of having that divide by 100, I'm thinking of it as decimals. And so this R becomes 1.037. So every year I'm going to multiply by 1.037, and that's the same as adding 3.7%. And so this time, though, I'm not asking for this person's salary after a certain number of years. I'm asking how many years will it take until they're making at least $100,000. Well, first, let's make my model for how much money we're making after n years. And that'll be my starting amount, 72,000. My common ratio is 1.037 to the power of n. Now again, if I go n minus 1, then I'm thinking of this being term 1, but I'd rather think of that as term 0, which is right now. And so I think that's easier. However, we're trying to figure out when this equals 100,000. That's really what we're doing. When does this equation equal 100,000? Now, to solve this equation, we do have an equation here, and you can solve this algebraically, but I have not yet taught you enough how to do that. We will learn this later if you take HL, but this requires learning logarithms, and with a bit of work with logarithms, it's not that time-consuming at all. But before that, and again, if you don't do HL, you never need to learn how to do it algebraically. We can solve this quite quickly by graphing. And I want to graph a system. I want to graph 2 equations. I want to graph this. So I'm going to graph one equation of y equals 72,000 times 1.037 to the power of x, I'll say. And I want to graph this equation, the right-hand side, as just y equals 100,000. It doesn't really matter what graphing device you use. While we should have a graphing calculator for a course like this, right now I'm just going to use Desmos. In my opinion, Desmos is way easier to use than just about any graphing calculator I've seen. And for just solving questions, I find I prefer to use Desmos. On a test, obviously, we can't use that. But this is not a test. And so I'm going to go to Desmos. And I already have those 2 equations typed in. You can see up here. Now, keep in mind, on my basic scale of my graph right here, I have my x-axis representing time in years, my y-axis representing the salary. So I clearly want to compress my scales a bit. I'm going to start with my y-axis. This is the annual salary. And we got to get well past these numbers, and now I can start to see a graph that makes more sense. And the y-axis, I can see years. I'm going to compress it a little bit. Doesn't really matter, but I can see right there. That's where the 2 functions intersect. That's the solution to the equation. And so I can see at just past 9 years, 9.042 years, is when this person will earn $100,000 exactly. However, we want to imagine, if you look back at the question, we want to imagine they're getting a raise once a year, not a tiny raise every day. And so in the end, although my solution algebraically, in this case it's n, although n is approximately 9.042, The question does say how many complete years. And so what this is not a complete, this is not quite 9 years. It's a bit more than 9 years. And so the answer will be after 10 years. This engineer will make at least $100,000. That's it. This is so close to 9 years. If you actually check and you put 9 into the equation right here and see what this person earns after 9 years. After 9 years, I checked, and this person is making just shy of $100,000, which is not surprising because it's just past 9 when they actually make 100. So at 9 years exactly, they're making $99,848 approximately. So they're extremely close, but it's not quite 100,000, hence we have to go to 10 years.